Technology being developed for driverless vehicles is pretty incredible. In the near future, there will be robotic cars traveling on normal roads with the safety and efficiency of the best human drivers. These autonomous vehicles use various sensors to be able to localize themselves in any environment. They are also then able to construct a detailed plan to get from their current location to any desired destination. This video will provide an introduction to how these autonomous vehicles are then able to follow their desired trajectories. Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper look at this in a lab setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang-bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in a car, since there is a range of angles the steering wheel can take. One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called the cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle we use is this cross-track error multiplied by a scaling factor called the proportional gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases, but at a cost. If you start too far away from the desired trajectory with a high gain, the system can spin out of control. With the best gains, proportional control returns better results than bang-bang control, but it still doesn't work that well. With proportional control, the car can be crooked when it reaches the center line. The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering command. A good candidate for an extra measurement is to look at the cross-track error rate, or in other words, how fast we are moving in a perpendicular direction with respect to the desired trajectory. If we are perfectly following the trajectory, our cross-track error rate will be zero. In control theory, this is what is called a derivative term. This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel against moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped, and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped, and will take a long time to correct for offsets. Properly choosing the derivative gain allows the car to approach the desired trajectory quickly with a cross-track error rate close to zero. This is called being critically damped. Despite the success so far, for a complete controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's nominal behavior and thus the performance of the controller. For example, if there is a heavy crosswind, the vehicle will drift unless the driver counteracts this wind force with a corrective steering command. Here is an example we can easily demonstrate. Imagine our vehicle is driving along and hits a pile of rocks which knocks its front end out of alignment, and therefore a zero steering command no longer keeps the vehicle driving straight. As you can see with the controller that has been described so far, the vehicle experiences a buildup of a lane offset, or a steady state error. One way to address this problem is to add yet another term called an integral term. This third measurement sums up the cross-track error to give an indication if we are spending more time on one side of the trajectory or the other. You can see that if we sum up the cross-track errors, we obviously spend more time on one side of the trajectory. The integral term we propose is then exactly this sum multiplied by a gain. Now, 3 gains will need to be tuned all at once, which can be quite difficult to do by hand. If the gain is too large, the controller can go unstable, because normal controller fluctuations will be exaggerated. If the gain is too small, it can take too long to respond to these dynamic changes. When the gain is just right, the controller will be able to quickly correct for the front-end misalignment and return to its nominal performance. The combination of these 3 terms is then what is referred to in control theory as PID control. There are other more advanced controllers that can be used for self-driving cars, but they will all look similar to the one we have described in this video. There will always be some measurements made about the state of the vehicle which are then compared to some desired vehicle trajectory to construct a steering angle that ultimately controls the car. Hopefully this gives some insight into the control strategies that can help make self-driving cars possible.